Hi, everyone. Welcome to You Got Potential, a podcast about research from the perspectives of undergraduates. So far, we've mostly been interviewing Rutgers students majoring in the life sciences, but that changes with today's guest, Anirudh Patel, a physics major and philosophy minor. Anirudh, would you like to introduce yourself and your project?
Sure. So I've worked in several areas of physics so far. Primarily my research over the past year, the junior year, has been in geophysics, where I study gravity anomalies and their implications in the Central America region, specifically in Costa Rica. More recently, this summer, I've been working on a particle physics project, high energy particle physics to be specific. And in the future, I'll kind of be working on an astrophysics and planetary science interdisciplinary project. So yeah, a lot of physics.
Hmm. So why was it that you ended up switching from a geophysics project to a particle physics project?
Sure. So the geophysics, so it was kind of just an opportunity that came up that was offered by Resty. But initially, when I came into college, my first 2 years, I was really interested in more so the environmental sustainability and environmental engineering and environmental physics. So the geophysics was kind of like a natural, segue into that because it's more, based on earth sciences here. And I didn't really have the intention of, or I didn't really know that I want to go into grad school for physics at that point when I was a freshman and sophomore here at Rutgers. But more recently, I guess, especially over this past year, I've become more and more interested in going to graduate school for a physics or astrophysics PhD. And high energy particle physics is a pretty, I guess, prominent research area in physics right now. I'm sure a lot of you guys have heard of the Higgs boson, and that's kind of that falls under high energy particle physics, and that's just really like a hot topic right now. So that was kind of the natural next step for me.
Can you elaborate a little bit more on what your current project is about?
Sure. So I started my current project, which is the high energy particle physics project, this May. So I can't speak too technically about it. Just the learning curve is somewhat steep, but just from a broader perspective, um, it's it's basically a project. So the experiment itself consists of colliding two very high energy protons moving close to the speed of light together, right? And this is done at the Large Hadron Collider, which is a particle accelerator located in the CERN facility at Geneva, Switzerland. And we collide these two protons moving very, very close to the speed of light. And it essentially produces a sort of reaction. And we know from Einstein that the famous equation E equals mc squared, where a lot of the energy from the speed of those protons is converted to mass, which forms other particles. So when these two protons are collided, they collide at around they collide within a detector, which we call the compact muon solenoid or the CMS detector. And that's the namesake of the experiment. It's called the CMS experiment. But the CMS detector essentially records and observes all the data that comes out of the collision. So all these different particles and things that are created from this collision, all that data is just recorded by the CMS detector. So our job as part of the CMS collaboration is to kind of go through this data. And it's a lot of data, right? So we basically have to parse through this data and try to narrow down the search parameters for various variables that occur during this collision. And we just kind of basically go through these variables. It's a lot of data analysis work and try to just narrow down the search radius and then try to find evidence for theoretical particles that have been predicted by theorists.
Hmm. So what kinds of theoretical particles are you looking for specifically, and what significance might they have?
Sure. So again, I'm just going to speak a little broadly about this, but the project that I'm working on specifically, we're looking for a theoretical particle called the Z prime gauge boson. But more generally, particle physics, discovering these fundamental particles has huge implications for helping us understand the origins of the universe. That's number one, because when the Big Bang happened, at that point, larger objects and larger matter wasn't really around. It was all particles. And there's a lot of matter and antimatter and particles and antiparticles and things like that. And just, discovering these new fundamental particles can kind of help us, kind of bring us one step closer to understanding that part of, our origin story. But more so, I guess, prominent to industry and the current world. Particle physics has a lot of implications for modern technology. A lot of the modern technology we use depends on these, on these particle physics interactions. So I think that's kind of a pretty big significant portion of what we're trying to do here as well.
Can you please give some examples of these like daily lives applications of particle physics?
Yeah, sure. So I guess when you go to a doctor and you get a CAT scan, right? That's, at the fundamental level, it's, requires understanding of particle physics. Radio waves, more radio waves and things like that. But I guess everything fundamentally just comes down to particle physics, and just understanding that better can help us just improve our technology in general. Yeah.
Thank you.
For the biologists and chemists, think the NMR machine.
Yeah.
The NMR machine, I think, works on the same fundamental principles as the MRI that Annie mentioned. I wanted to ask a little bit, pick your mind. How'd you started? I remember you talking about it a long time ago, how you got that opportunity with the Rusty, what that process was sort of like, and how was your time there?
Sure. Yeah. So Rusty is a great program. I think it's really for Rutgers students, especially for Rutgers students only, I guess. But I think my first Rusty project was actually different than the geophysics one. I got involved in that my sophomore year. It was kind of like an environmental engineering project. I won't get too much into that, I guess. But the geophysics project. So during my sophomore year, I just kind of noticed that there was an ad or I guess something like that about that project. They sent out an email, and I was like, oh, cool! Like, this is a cool project. I'm going to get to travel to Costa Rica because it's based out of Costa Rica. So I was like, this is a really cool opportunity. It's also kind of aligns with my goals. So I just applied, and I went to the interview. And actually, one of the people who were interviewing me was one of my the undergraduate program director for physics at the time. So I had known him, just through advising meetings and things like that. So I guess I was a little less nervous at that point because there were like 4 or 5 people interviewing me. But yeah, I gave the interview, and next thing you know, a few weeks later, I got the position, and that January of my sophomore year, we just started, having seminar meetings just to like prep us for the project, which would take place, start over that summer. And over the summer, we were planning on going to Costa Rica for the project, but unfortunately, due to COVID, never really made it down to South America. Yeah, it's pretty sad. I still get kind of sad when I think about it. But yeah, so the point of going to Costa Rica was to work with our international mentors from the University of Costa Rica. So I worked with Dr. Oscar Luque in gravity anomaly work. So we would have been going to all these huge mountains and bring these huge tools called gravimeters with us, which would measure the gravitational acceleration at some of these remote regions in Costa Rica. And that kind of leads to the next step of the project, which would be the part that we would be doing over the year, my junior year, which was this past year. And that consists of basically processing and analyzing that data and making models. So I guess just to give a quick overview of what the Costa Rica project entails, we basically, like I said, go to we're supposed to go to Costa Rica, collect this data, this gravitational acceleration data, and we try to use this data to model the subsurface features of that region. So the specific region in Costa Rica we're concerned with is the Cordillera de Talamanca mountain range. And we're interested in that region because, that specific region of Costa Rica lies above a subduction zone, which is where one tectonic plate is subducting beneath the other tectonic plate. Specifically, the Cocos tectonic plate is subducting beneath the Caribbean plate, which is where the Costa Rica landmass lies. And due to that subduction zone, that's why these, mountains were created. And we kind of expect there to be a lot of volcanic and seismic activity in the region, but we don't really see that when we, in our observations. So to try to kind of explain these anomalous features, we're trying to, we think it has something to do with the underlying structure of the crust and mantle of that region. So essentially, we know we can predict, based on standard density models of the Earth and standard composition models, we can predict that, this region should have a gravitational acceleration of, some amount at the surface level. But when we actually measure the gravitational acceleration with these gravimeters at the surface level, we find that, the observed gravity values don't match up with the predicted values. So then we think, okay, there has to be some anomalous feature beneath the surface that we didn't really expect. And so what we do is we use this gravity data to kind of create models and play around with the density of these subsurface features to try to find a model that would create the gravity values that we're looking for, and therefore reconcile the anomalies.
Going back to a point that you mentioned a while back, you were a philosophy minor, correct?
Yeah. So I'm actually double majoring in philosophy.
Oh,
yeah.
So what led you to pick philosophy as a second major?
Sure. So I was always interested in philosophy when I was in high school, and I was kind of always interested in those big questions. And I guess like as a high schooler, I was like, oh, if I major in philosophy, I'll figure out the meaning of life. And I quickly realized like that's I'm not going to figure out the meaning of life by majoring in philosophy, because oftentimes one question just leads to another, and it's kind of like a recursive cycle. But I would say Rutgers does have a really good philosophy department, so I think as far as technical skills I've learned, just reading and writing and critical thinking that's really helped me with that. And some of the big questions, I don't think they've been answered, but I think I can, I'm starting to learn more from, previous philosophers and kind of just form my own opinions and viewpoints on stances and philosophical issues.
What other like skills or mindsets do you think you can carry over into your future work, like in your potential PhD that you want to pursue?
I think, yeah, so I think another big part of research is persistence. I'm sure you've all experienced this as well because you guys are also undergraduate researchers, but oftentimes things can kind of get pretty tough. Maybe you're at some point where you're just not really making any progress. You're having a tough time, moving on to the next step, or you're just kind of stuck on this one paper and you just can't understand, what's going on. Or something new comes out and you just don't really see how it matches with what you know about the field or your own research. And I think at that point, I think persistence and just kind of sticking through it and just grinding through the process of spending those hours performing your work or analyzing your data or reading these papers, I think that's where that persistence and that kind of hard work and dedication mindset kind of comes in. And I'm sure, as I go on in my research career and as, all of us go on as well, I think that's like a pretty valuable and fundamental outlook to have.
Mm-hmm. Yeah, it kind of illustrates an interesting challenge to research, and that is, you have to be very determined, but you also have to be careful about underdetermination. So you spend all this time fine-tuning a model, but at the end of the day, this is just one guess out of many, and it's important to be open-minded enough to put your pride aside and say, guess I was wrong here about this. Guess it maybe worked for this set of data, but not the most. How do you think it is that in your case, you strike a balance between the two?
Yeah, so let me just think about this for a second. That was a good question. Yeah, I think it's tough because you want to have confidence in your own work and your own work and your own models. But at the same time, like I mentioned, you want to keep an open mind towards other work as well. Or But I would say, when there's a discrepancy between some results that you may have and some results that somebody else may have, I think, the immediate reaction would be to go back and immediately just check if I made a mistake, right? I think that's, generally the first thing I do in situations like this, because, it's one thing to have confidence in your own results and your own work. But, at the end of the day, we are all human and we do make mistakes. So, you might go back and you might find something, oh, okay, like I didn't make a mistake, right? Or you can look at the other, the opposing models, not opposing model, but the alternate models approach. And, you might see that, okay, they did something different, right? Maybe they used a different set of constraints. Maybe they used, slightly different process data to achieve their results. And maybe what they did, maybe that method was more robust than my method, right? So that doesn't necessarily mean that, what I did was not correct or was, kind of, it doesn't mean it's worthless, but it means that, there was a better method out there and maybe I should implement that method in my work and maybe see if I can come up with a result that's, that verifies what they have, or maybe I might even come up with a better result, you never know.
I wanted to know, Annie, I assume it's your high energy particle physics work. What sort of got you moving in the astrophysics direction versus geophysics or anything else? Georgia, were you going to ask that? I'm sorry.
It's like 20 minutes ago, but I'm glad you asked it too.
Yeah, so actually, the particle physics wasn't what got me interested in astrophysics. I know it sounds that way because I did geophysics and the particle, and now I'm kind of interested in astro. But last fall, I took a class. It was a planetary sciences class offered by the Department of Earth and Planetary Sciences, which previously used to be the Department of Geology at Rutgers. But my advisor for the geophysics work, Professor Vadim Levin, was co-teaching that class with a new professor, Professor Catherine Birmingham, who is actually going to be my advisor for my astrophysics work now. But that class, it was called The Structure and Formation of Terrestrial Planets, right? So Dr. Levin, who's the geophysics guy, he comes in at the structure part of the story. And Dr. Birmingham, she's a cosmochemist. So she comes in at the formation part of the planets. And we kind of reviewed basically how our solar system formed and how our planets in the solar system formed. We talked a lot about Earth, of course, but also Mars, the moon, Jupiter, and all these different planets. And that's kind of what really piqued my interest in astrophysics. And because there's it's a very interdisciplinary field, right? As you can tell by her PhD, cosmochemistry, it's a very niche, but also a very interdisciplinary field. And she works with astrophysicists, geologists, planetary scientists. It's very there's a lot of things that go into there. That's kind of what started me kind of on the trajectory towards astrophysics. And kind of now,
have to email her.
Yeah.
I'm gonna have to email Cosmo.
Cool.
I think we talked about this, and I still don't know what it is, but it sounds crazy. It sounds crazy cool to work with physicists.
Yeah, it's basically geochemistry except in space, but yeah.
Yeah, when you said cosmochemist, I think like my eyes got wide. I saw George's eyes got wide. Then Kat was just like, what the heck?
Yeah, I had never heard of that before I met her, but yeah.
Do you have like your own like potential niche area that you want to work in astrophysics, or are you just keeping an open mind for now?
I have a pretty open mind for now. So, after I took that class, I was really interested in planetary formation and planetary dynamics, because those inevitably, dynamics especially, just kind of just uses, physics. It's very physics heavy. But then I kind of became, my interests are still, progressing and evolving. But then I really became interested in like stellar astrophysics, right? Like stellar formation and stellar evolution. And the project I'm going to be working on next year for my senior thesis with Dr. Birmingham, kind of has to do with the production of different elements in stars, and how those elements that were produced in stars prior to the formation of our solar system, how they contributed to the origin and evolution of our planetary systems. And then now with particle physics, I'm kind of also becoming a little bit more interested in the cross section between astrophysics and particle physics, which is astroparticle physics, or high energy astrophysics. But yeah.
How are you going to study that for like your thesis? Is it like taking an experimental, or I don't know, theoretical data and
Yeah,
that doesn't
so no, I know what you're saying. So so right now I'm just doing a lot of background reading just to prepare for the project next year. But the project itself, I think it's a combination of using data and using theoretical modeling and computation methods. So the data we use comes from these meteorites, and we sample the meteorites, and we're able to find isotope and chemical data from these meteorites, which kind of will tell us, okay, like these are the elements that are out there in space. We kind of then you can use like radiochronology methods to be like, okay, these isotopes were in these meteorites and they're older than our solar system. So these kind of preserve a kind of historical, I guess, what's the word, record of the processes and things that happened before our solar system was formed. So that's where the data comes in. And then the other aspect of it is the theory and computation, right? So, we'll see, certain elements and isotopes in materials that we observe or analyze, and we'll be like, okay, where do these materials come from? And that's where we kind of, run computational models of supernova and stars and things like that, because a lot of the elements that are in our solar system came from these high energy and high entropy or low entropy, on the other hand, environments in stars and supernovae.
I would like to ask you something that we talked about very early on, which is you didn't know at the beginning of your university career that you were going to go to grad school or think about going to grad school. What was the pivotal moment of your years as an undergraduate student that made you realize that's the place where I would like to see myself? And if so, do you know at this point in time future directions after grad school that you would like to take?
I would say the pivotal moment, well, definitely happened over the past year. Because I feel like when you're a freshman, sophomore, you're just kind of concerned with, okay, what classes am I going to take next semester? Well, at least I was. I'm sure not everybody, is, some people probably think more ahead than I do, but that's my outlook as a freshman, sophomore. It's like, what classes am I going to take next year? Like, I had to do well in my classes. I'm going to find research, whatever. But then, along came junior year, and about halfway through my fall semester, I was talking to a lot of my friends who are in finance and other fields in software and tech, and they all have internships lined up. And I was like, oh man, like, I started getting a little nervous. I started panicking a bit, and I had this kind of existential crisis. I was like, oh my God, like, I didn't really think much about what I wanted to do after I graduate, but do I want to go into industry or do I want to go into grad school? And at that moment, I was just kind of, I spent a lot of time thinking about it. I guess it's another way the philosophy major has helped. When I have a problem like that or a dilemma, I get really like flustered and I start to panic, but then I kind of just think on it for a week or maybe 2 weeks, and eventually the answer will just kind of like become clear to me. In the beginning it seemed so hopeless, right? I was like, oh, there's no way I can like make a decision like this. But 2 weeks later I'd be like, okay, this is definitely what I have to do, and this is what I should do. So it was kind of that type of situation where as I just went on in my crisis, I kind of realized, I've done physics for, almost 3 years now. I initially it was tough, it was a love-hate relationship freshman year, I'm just working and doing homework all the time. But now I think I've really grown to like the topic and I really love it. So I can't really see myself doing anything different than, pursuing it further in graduate school. And as far as my aspirations after graduate school, again, I'm not really one of those people that think that far ahead, but I would say, I'm definitely interested in being a professor at some point and a research scientist. So that's kind of in the scope of my future, I guess, hopefully.
I'm intrigued as a person that is doing a major in science. How is it to be a physics major at Rutgers? Is it like a big major? Are there many resources? One thing that I'm particularly interested in is that so far we've talked about three potentially relatively different fields in physics. But to my knowledge, there is like physics major. There isn't like particle physics major. I could be wrong, but like, you know, within life sciences, there's like just biology, genetics, molecular biology. Then you go back to like, I don't know, somewhere in Cook Douglas where there's some other cool way of putting life science. So how's the physics like world?
So the physics department at Rutgers is excellent. You know, I've been very happy with my education at Rutgers, and like all the professors that I had are great. And I've learned so much. So I'm really happy with that. Rutgers does have a, you know, really good physics program. As far as the majors go, so there's 4 different physics majors. They offer a minor and they offer 4 different majors. There's a general physics major, which kind of like, you know, you take gen physics and maybe a few other advanced physics courses, but it's more just like surface level. And that's like, you know, if you want to go into education, or if you want to like, you know, if you want to be pre-med, or you just want like a little bit of physics background, that's kind of what you would do. Then there's applied physics, which is kind of like, it's very similar to engineering, right? You can take, you know, kind of like the core physics classes, and then you could concentrate in some area of like, you know, it could be chemistry, engineering, biology, or something else. And then there is professional physics, which is the major that I am, and that's really to prepare kids for graduate school. So that's like, you know, you take the really advanced physics courses. For me, I started off with the honors introductory sequence, like honors physics 1, honors physics 2, honors physics 3, which was essentially physics boot camp, extremely difficult classes. But yeah, so the professional physics is where you're, you know, required to take, you know, more labs, more of the upper level physics courses and things like that. And then we also have a separate astrophysics major. So that's similar to professional physics. It prepares you for graduate school in astrophysics. And obviously that's, you know, the classes you take there are geared more towards the astronomy and astrophysics side of things.
Thank you so much for your answer. I would like to really thank you for, first of all, spending time with us today, and second of all, for being such like an open and curious mind that makes research thrive so much. I think the world benefits from having people so curious and thrilled to learn. Yeah, again, really, thank you so much for being here today.
Yeah, thank you guys. I mean, it's just, I think, you know, this is just like a great program that you guys are running, and thank you guys for just reaching out to me and kind of giving me an opportunity and platform to talk about my work. And yeah.
I would like to wish you all the best for your future in your last year at Rutgers, and remind you and all the listeners that you've got potential.